Hello everyone, welcome back to our channel. So today I'd like to show you guys a little bit about the design of reinforced concrete beams. This is one of the first lessons that I'll be teaching this in English due to certain demands on this type of subject. The design of reinforced concrete beams, it's actually very simple. Okay, today we are going to talk about pretty much the flexure theory that is behind. And then we're going to talk about specifically the theory of concrete flexural theory, okay? And then we're going to do one example, which is this one. And after we're done designing sections with only one layer of reinforcements, I will make some comments about other types of sections. And in the lesson 2, we are going to learn how to design sections with also compressive reinforcement. All right. If you have any questions, please just let me know in the comments below. Okay. So let's just start with the regular flexure that we usually have on beams. Suppose that we have a single supported section, and let's just consider that it is a homogeneous material, okay? Which means that the whole material of the section, it does not matter. It can be a concrete, it can be steel, it doesn't matter. Let's also assume that there is like a pointing load at the middle of the span, okay? And whenever we see this happening, this point load, it will actually create flexure in the beam like this. So why is this important? So as you can see here, from this very exaggerated deformation, we can see that the top part of the beam is going to be under compression. Okay, if we collect like a molecule here, this molecule right underneath the P load is going to be under compression, as we can see here, due to the strain. And then the other part, right here at the bottom, there is going to be tension, okay? So if we collect an atom pair and we look into it, it's going to be under tension, right? So what this is actually telling us is that from the most top layer to the lowest part of the beam, there's going to be a strain gradient, which means between the top and the bottom part, there is going to be a part of the beam that will not have either tension or compression. This part here, it's what we call, let's just say it's C, but it's the neutral X. The neutral axis is actually what it calls, it's neutral, it does not have compression or tension, okay? Suppose now that we're going to make a cut here, it's an imaginary cut, we're not actually going to cut the beam, and let's just call it this section, which is going to be section AA. When we see here, if the point load is exactly in the middle of the span, part of this P load is going to be supported by one support, and half of it is going to be to the other one. All right. So we would have this. Looking to the left side of the beam, part of the load is going to be upholded by the left support. When we do like a virtual section, of course, the section will be holding bending moments and shear forces. If we remember a little bit about the bending moment, remembering that this is specifically for American students. In the US, the bending moment is actually in the opposite of the rest of the world. So bending positive, it's above the X, and negative, it's below the X, right? So since it's a point load, we have here the zero part, and then since it's a point load, the reaction P2 is going to be linear increase until reaching the maximum bending load, which is going to be when X is substituted by L over 2, we're going to have PL over 4, okay? So that's the maximum bending moment. For uniform bending moment, we're going to see by the end of this lesson, okay? So coming back a little bit on the flexure theory, suppose that this beam has a rectangle section, okay? So its height, let's just call it h, and the width, let's just call it b. So as we said, during this deformation, we will have a strain at the top of the section. Let's just call it compressive strain. And at the bottom, we're just going to call it tension strain. All right. So whenever we have this strain in the section, we know that stress equals to the elasticity modulus times strain. Okay. So whenever we have strain, the material has some properties. We are going to have stresses. Okay. Oh, all right. So whenever let's just call it a section or a member or a component is under strain, will it will generate stress. Okay. And if we have a flexure theory in which we understand that we see that the strain is actually linear. Okay. This is a few things like as we consider the flexure theory. It's stress, usually they are linear elastic. Also, other things we consider the Bernoulli hypothesis. The Bernoulli hypothesis is just pretty much sections will tend to not have any curvature because whenever we see a bending in a beam, it's actually very small for a concrete section. So we consider that the section will not like translate, all right, or will not curve, okay, under this scenario. So whenever we have the strain here and the stresses, they will uprise. We see that the rectangle section, the axis is actually divided by 2. Okay, so the neutral line is actually exactly in the middle depth of the section. So when we get this strain and the stress distribution, since it's a triangle shape, if we have stress, we are going to have also a force, right? Because we know that stresses are equal to forces divided by a section area. So forces is equal to stress multiplied by area. All right, so we can describe this triangular block of stress with a force that we're going to call it just capital C. Okay, this force, which is its center of mass in a triangle, is going to be around 2/3 of its height. So we have this distribution here. Okay, and Yuri, why is this important so far in the flexure theory? Well, this is what we call a stress block. The stress block idea, we are going to use this also in the reinforced concrete design. If you may, let's just see in a three-dimensional environment, this triangle section that we are going to call it stress block. The stress block volume is actually it's half of the height, the width of the beam, and we also have in the top part of it, we just call it the compressive stress, right? If we get this volume, which is a volume of a triangle, and we multiply by the stress, we are actually going to have the compressive force in the center of mass of this stress block. So doing the calculations here, which is quite simple, we know that it has a triangle shape, so it's height over 2. Let's just call it here the stress of the force divided by 2. And the volume of this triangle is the half of the section multiplied by b. Okay. If you guys have like any questions so far, or if it's getting very confusing, just let me know in the comments below if you have any concerns about what we're doing so far. Okay. And also, whenever we're designing a beam, we usually tend to have 2 other measurements. The one is the y. The y is actually the distance from the top to is the distance from the neutral x towards the most outer part of the fibers, which it would be this guy here. That would be maximum distance y. Okay, so the distance between the center of mass to the most hour uh, stressed fiber, okay? And usually for a rectangle section is pretty much h over 2, so half of the section's height. And if we just isolate h, h would be 2 times the distance to the top fiber. And the other units that usually we assess during flexure is the inertia. The inertia of a rectangle section, if you remember in your class of mechanics, is the width of the section times the height uh, to the third divided by 12. Okay. If we also divided everybody by h, we're going to have this inertia over h. It's going to be b times h squared to the 12. Okay, we're going to use this later on. And lastly, what we want to guess is actually how much can the beam bend. And for that, we want to what we call, let's just try to understand this concept, is determine how much bending moment can it support. So for the flexure theory, as you guys saw, if we have a linear distribution of the strengths, what we have here is that on the top part of the triangle, we have the compressive force, and at the bottom part of the other triangle, we're going to have the tension force. This force is to generate equilibrium. Of course, C has to be equals to T. Okay, otherwise you would not have equilibrium. And remembering, the C force is two-thirds of h over 2 from the neutral line, and the T is also the same thing, two-thirds from h over 2. Okay. So the what we call the lever arm here, let's just call it J. J is going to be 2 times this guy here. All right, so let's just cut, and 2 times this guy, so 2h over 3. Okay, this is the lever arm. And lastly, the bending moment, all right, let's just call it a bending moment in this part here. Is going to be the C times the lever arm. Or on the other hand, if you'd like to check the bending moments here, you just check the force T times the lever arm. Okay, so that's what we know how to calculate the bending moment. All right, so it's bending is the arm multiplied by the force, which is the same, right? So if you cut here, of course you would have equilibrium. Okay, so the bending moment or the nominal resistant moment here, it's very simple to calculate. We checked the C force, which we saw here previously on the concrete stress block, is the volume of it multiplied, right, by the other guys, which is right here. Let me show you guys here again. This one, all right, this guy here. All right, so let's just put all that. The J, which is the lever arm, is 2h over 3. And the force, which is the C, it's the stress, compressive stress, divided by 2, multiplied by h over 2 times b. Okay. If we reorganize this equation, let's just leave it 2 times concrete stress, and what we're going to have is h multiplied by h times b, so h squared divided by 12. Okay. As you guys saw previously, what we did, this part of the equation, it's actually inertia over h. It's right here. So this guy here is inertia. So what we have so far is 2 times compressive stress multiplied by I divided by h. And we also saw that the height of the section is 2 times the distance to the compressive strength. So this is equal to 2y. So we would have now in this equation this part here. Right? If we cut this guy with this guy, what we have left is the compressive stress multiplied by inertia divided by y. If we also reorganize this, we're going to have the flexural stresses. Okay, so flexural stresses due to bending is going to be m bending moment times y divided by inertia. Okay, so you have seen this equation previously in probably your mechanic classes, and this is how we actually do. So the idea behind the flexural theory is actually understanding where we're going to have compression and tension, what is the definition of bending moment, and how can we determine the forces in the stress block. So from now on, we can actually go to the next part of this lesson, which is going to be the concrete flexure theory. I'm going to stop the video so this video will not be that long.